Welcome to this first lesson on Applied Network Science to Maps of Science. In this first lesson, we are going to present an introduction to the network science, and in particular in this video, we are going to see the historical evolution from graph theory until we arrive to speak about networks. So we are going to speak either about networks and graphs, and we are going to consider them equally. In any case, we are going to speak about the structures in which we have elements that we can identify with the people, and these elements are connected by some type of relationships. It depends if we are speaking of networks and graphs on the approach, if we are speaking more from the data part on the structure as the complexity of the connections, we're speaking more about networks, and if we are speaking about algorithms to find paths between this structure, we are going to speak about graphs. Network science deals with this complexity of the relations, and it has its own terminology. The elements will be called nodes or vertices, and the connections between the elements will be called arcs or edges. And we can have a sense in this relationship or not. So for instance, if we are speaking about Facebook, in Facebook we have that the people are the nodes, are the elements, and they are connected, and the connection is reciprocal. Two people, if they are connected each other. However, in Twitter, we have that the connections are on one way. Of course, you can be connected in two ways with another people if you follow each other, but intrinsically the connection is directed. Another example that we can find is about road maps. We can say that the cities are nodes, and two cities are connected by an edge. We can find a trip or a road that connect both cities. In this case, if we are considering highways and we can go in both senses, we can say that the connection or the graph is non-directed. But if just we are going in one direction, we are considering only one-way roads, we can speak about a directed graph. Here I have also shown an example about other appearances of graphs in culture, and here I have put some image of Big Bang Theory where Sheldon is speaking about an extension of rock paper scissors game, which is rock paper scissors slicer spoke. Here what we have is that each node is represented by one of the figures that we can do with the hand, and what we have is that they are directed. We have arcs from one to the other if one beats the other. For instance, if we look at scissors and paper, we have a connection from one to the other, and it is because a scissors cuts paper. And since paper covers rock, what we have is a connection from the paper to the rock, and we can follow with the rest of the connections. So it can be studied that as rock paper scissors, this game is equal for all the participants because we have an odd number of nodes, and you can appreciate that each node beats two other nodes and is defeated by two other nodes. So the study of these connections and the study of the connectivity was interested or emerged when we have great amounts of data, and in particular it emerged with the advent of internet and of social networks, because it provides answers to questions that were long standing, and people were thinking about how are the structure of these connections. So if we want to study about how the connections were done, you can think about a party, and in a party when you arrive, if you don't meet each other, so you start to speak with few people, for the ones that you probably arrive at the same time, but as long as the party evolves, what happens is that all the people start to speak to each other. So it's, for instance, here you have an example of one of the properties that is studied by network science, which is the emergency of the connectivity. At the beginning on the left, we have isolated groups of people that are not connected, but it happens that if you count the connections and the number of people, at some point it will arrive that most of them are connected. And this is a property that can be studied and illustrated in these networks or connections of networks. The first one who studied the connections from a statistical point of view were Paul Erdos and Alfred Renyi, who introduced random graphs. So random graph works like this. You have a set of nodes, and what you consider is a probability P. And what you do try is you pick every pair of nodes and you make an aleatory experiment, random experiment, and if the value is between 0 and 1, if the value is smaller than P, what you do is you connect the nodes, and if the value is higher than P, you don't connect the nodes. So what it happens is that taking into account P and the number of nodes, it arrives to a point that most of the nodes are connected. So for instance here, with this amount of nodes for P, they are most of them well connected, but with P equal to 0, 2 is clearly they are connected. In the distribution of nodes, the typical distribution for random graphs is the following. If you consider the size of a node that is represented in the x-axis by the value k, and you consider by the pk the number of nodes of site k, what you have is that most of them have the similar amount of nodes and the similar amount of connections that will be represented in the middle of the bell shape. And what you have is very few that have very few connections and very few that have a lots of connections. So at the beginning, it was thought that the connections between people, they will probably be following this pattern. But despite these papers of the 70s, in the 50s, Cohen and the Solapool start to think about how are the connections perform and how can be studied about this. So what they try to show is how people connect with each other and how can this modelize. And this was dating from a time where you cannot have a list of all your colleagues and you cannot mix with the list of all your colleagues as Facebook does now. So this appears in a paper nearly in the 80s, but this manuscript was for nearly 20 years with a list of questions that were trying to set how to define the problems that have to be considered. So before this, even in psychology, Stanley Milgram studied how were these connections, and it's very well known the theory of the 6 degrees of separation. Here, what the experiment that he performed, considering a random selection of individuals that were living in Sharon, in Maha, in Nebraska, and they were kindly asked to send a letter to certain people that were target individuals in Sharon, Massachusetts. And they have the name of the target person and the occupation. And what they have to do is to pick a package and to send to the person that they will think that it was closer to know them. So think that they have information just about the name, the occupation, and the place that they were living. So they will probably start it to send to someone to the East Coast or to the Middle East and later to the Boston area, and in the end they will arrive to try to connect to the people. So 20% of the initiated change reach the target with a change of approximately 6.5. And the name of 6 degrees of separation comes from this, and also because formerly it was at the beginning of the 900s theater show or play that was called 6 degrees of separation and was speaking about this fact. And this number was incredibly unexpected to be so low. This is what is called the small world phenomenon, and it's referred to the Milgram's experiment. They even found very interesting things, that they were in several cases the last person before arriving to the target person was the same. So it happened that there were people that it seems to me to know a lot of people, and people try to reach these people to get the connection. This theory has been considered in other in other cases, and one of them was the 6 degrees of Kevin Bacon, which is about the connections between actors, and it's like it started early as a joke with Kevin Bacon, and later it was developed a game, and I have uploaded a video where Kevin Bacon in fact explains how this affected her life and what is the impact and how he tried to get profit of it. We know already that this theory of the 6 degrees of separation is even lower, and analyzing Facebook data, what we have is that this even below the 4. But the thing is that this can be achieved because we have a complete list of all the connections, and this permits to perform the experiment. The study of social networks through graph theory, one of the first works was the work of the Zachary's Karate Club. So here in what Zachary studied was a karate club with 34 people, and it has two prominent figures. The number one, who was the Mr. High, who was the karate teacher, and the number 24 that was the administrator of the club. So it happens that this club is split into two parts, and he tried to know if there can be predicted how this would be split. The point was that the karate teacher asked for more money, and the administrator of the club doesn't want to pay more because it was an university club and it wanted to have low rates, low fares for the people. So what he did is, in the beginning, he tried to connect all the nodes and represent each person by a number, and if two people were connected, what they put is a 1. So if 2 is connected with 1, we have a 1, but if 2 is not connected with 0, with 5 we put a 0. And here this is in the matrix on the left part, and in the right part we have a graphical representation of this situation. But he advanced, and he also considered the following. Let's go to quantify how strong are the connections between two people. So what he did was to take a list of 8 questions and to ask for each pair of people in how many of these interactions they agree, because his assumption was that the more you coincide with someone in different settings or frames, the more closer you are to these people, and the more easier is that you both take the same decision. So for instance, 2 and 1 coincide in 4 of these items, but 2 and 3 coincide in 6. So 2 and 3, so the decision of 2 will be closer to the decision of 3 than respect to the decision of 1. Okay, so with this information and study these connections, what he applied is an algorithm which is for Fulkerson, that it permits to see, given two nodes, what are the closer to each one, and he predicted this scission of the group. And it happens almost by the case of number 9. The situation of number 9 is that he was addressed to another group of people, but he even went with Mr. High. The point is that he was about to get the black belt, and despite his friends were in the other group, he preferred to keep on with the Mr. High, the karate teacher. So these were the first studies about the social networks, and one of the landmarks or the cornerstones of this theory was the work of Batts and Straurat. They realized that the model of Erdos and Renyi was wrong because they inhabilitate the small world property, that people can be connected, very different people with few links. So what they perform is a mixed model between where you started with a regular graph, that is the one that you have at p equal a 0, and a regular graph is a graph where each node has the same number of connections. You can appreciate there that each node has 4 connections, and in order to get the small world, what they did was to break some of these connections with certain probability and to set new connections with nodes far away. And in this case, breaking some of the connections, what you can do is to reduce hugely the number of steps that you need to connect people. So let's suppose that you are living in the States and you are living in Spain. So if you want to connect the people and two people in one of the countries know the same people, so it will be easier to make closer both groups of people through that person. And this is the part of how the small world works. Of course, if the value of p is increasing and arriving to 1, what you will arrive finally is to a random network. So in the middle between a regular and a random network, they found that you can find small world networks. And a year later, Barabasi and Albert, what saw is that it can be, they studied the connectivities of various large networks, such as the actor collaboration network, where two actors are connected if they meet in one film, the World Wide Web, and the Power Grid data network. And what they saw is that there were a pattern that a large network follow a scale-free power law distribution. That means that most of the nodes have, or very few nodes have a high degree, and very few nodes have, and very large nodes have a lower degree. And what if you see is this representation follows more or less the same pattern if we are looking at the logarithmic scale. So what they conjecture from these models is that in fact what happened is that there are very few nodes that are highly connected, and most of the nodes are very few connected and with very few nodes. And it happens that in these cases the distribution of the degrees follows the pattern that you have on the right. So the probability that you have nodes with few connections is very high, but there are nodes with some significant below probability of having a large size or a large number of connections. Okay, so what it was is like it happens that random distribution is not and it has been a research area that has been developing very intensively during the last 20 years, is not the correct way of describing real life phenomenon, and the power law distribution in many cases is more suitable. There are also another networks such as hierarchical networks, but by now we will leave here. And just to end, we will have here a representation in which we can study how are these patterns of the connections. And as you see, we have included here also the protein interactions network, and the pattern in all the cases is the same. So the point of view of network science is to study this phenomena of complexity that permits to emerge properties at larger scale if you are just studying local properties. And by a local property, we are meaning that you are just studying how a node connects with the rest of the nodes. And this is all for this video. Thanks.